Good morning. Welcome to the ZoomTown experiment. I think we're up around episode number 45. Forgive me, I'm actually losing track lately. Last episode, we talked about how I can communicate from the Zoomie over to the scheduler the location where it currently is, part of our Zoomie tracking system. Now, with the scheduler having that information, that can serve as a sensor that the Zoomie can contact and say, I need information about, just like any other type of sensor. We use that now for our encoders, our collision avoidance sensor, etc. We query it for some piece of information, it gives us information. So that's how we're evolving the scheduler right now. Now, this next part of this construction, so to speak, within our whole system has to do with a focus on more collision avoidance. And I had a plan originally going back about a year when I was conceiving this whole experiment, and I thought, that shouldn't be that difficult. We'll just do it this way. As things evolved and developed in the course of almost a whole year now, I've come up with a different idea, and this popped into my head very recently. So I want to discuss this idea with you and see what your thoughts are on it. This will be mostly just a slideshow presentation with me providing commentary over it. So be a little different than my normal presentation, but I think it'll help convey the concept better and more clearly, and hopefully enable you guys to have a better comment or a stronger comment on what you think about doing this. So we're going to start right away with the presentation. The ZoomTown may be tiny, but there's plenty of places to crash. Here on the layout, and this is a scaled diagram of the layout, you can see 16 different Zoomies on here. And in some places, they're pretty crowded. Other places, not so crowded, but very potential for a crash there. Here I've got a Zoomie turning left. This Zoomie could easily hit it. This one is going to get up here and turn either left or right. This guy could hit it. All around, there's a lot of ways for Zoomies to crash into each other. And our CAS system will help with a lot of the most basic crash conditions. But the majority of these crash conditions truly involve turning. My original concept had to do with just using math to look at the proximity of all 6 or 15 other Zoomies. In this case, this is the one at the center, and this is the one that's making the left turn, which would be presenting or creating a crash condition. Now, the math is very simple on this. Pythagorean or trigonometry can make very quick help of doing how far over, how far up, and the as the bird flies, direct distance between the two components or objects. Well, that was a great idea when I started, and mathematically it's very quick, efficient, easy, and the schedule should have no trouble with it. But when you start taking into the complexities of all the different Zoomies in different states, parked in a driveway, driving along straight, making a turn, hiding around the turn, on the other side of the whole block, on a completely different road, suddenly that whole concept gets very deep. You would start out with a known distance based on time. And we'll get into that here in a little bit. But in a certain period of time, any Zoomie can move X amount of distance. Well, then that is a threat or a potential for crash. And so what I would need to do, based on some very simple calculations, is need to know where any Zoomie is within 24 inches. And that could be in a huge variety of locations. Now, what I've got drawn here is actually pretty close to scale. If this is a zoomie turning left, these are all the other zoomies that are within that 24-inch range. So now it starts getting more complicated. Well, if it's within 24 inches range, okay, that's a concern. But then, is it on the same road? Well, yes, or maybe no. Well, yes, it could definitely be a problem, especially like in the case of this zoomie. But what about this zoomie? He's not on the same road. In fact, he's around a corner and on a completely different road. Now, but in 24 inches, within X amount of time, that zoomie could very well be in a position to crash into another zoomie. So as I'm actually writing this code a week or so back, I started to really think about this, and I'm thinking, we're doing an experiment. We're working on an alternative method of transportation, so I don't have to follow all of our given rules. I can make up my own rules because we're experimenting with an alternative system. Now, traditionally, and just to help keep things straight with everybody from all over the world, I'm from the U.S. We drive on the right side of the road, which in my opinion is the correct side of the road. So our left turns are our most hazardous turns. So in this case, if I'm traveling along over here and I want to make a left turn, it is my responsibility to wait until traffic is clear before I proceed. Well, that's kind of polite, safe, works well with the person right there and instant reaction times and all that. But I think there's another possibility in the whole mix of this. Let's take a little closer look at our collision avoidance system, see what its strength is and what its weakness is. Its strength is it can measure the distance between this zoomie and another zoomie or any other object that is straight ahead. Now, where it gets a little trickier, here is a picture of a zoomie, or we're using an arrow as an icon for the zoomie, like up here on the roadway, and that purple triangle is its field of view. It's very limited. Now, it's hard to actually get accurate data off that data sheet because of the way they've got it drawn. So I went into CAD, created this drawing with a total of 6-degree spread between the two angled lines. And I picked two distances. Say the zoomie is here, moving away. At 8 inches, our beam width, our field of view, is only 0.8 inches, about 20 millimeters. At 20 or 19.5 inches, which is almost 500 millimeters, our beam width is 2 inches or about 50 millimeters. Now, to help keep things in scale and perspective, up here on the drawing, we can see the car coming along this way. That could be coming up on the blue car about to turn left. So it can kind of see it for most of its travel. But as it gets around the corner, the back end of the zoomie still could be hit with the left side of this zoomie because it doesn't see it in that purple area, the beam width. Now, coming from the opposite direction, a car going, or a zoomie in our case, going towards the turning car, it will see it when it's fully broadside, but it won't see it when the nose is just entering the intersection or the tail is just exiting it, at which point either this side or this side of the zoomie could hit it. So that's its limitation, and it can't see around corners, which will actually create it can kind of see around corners in certain conditions. And that's the subject of another whole conversation further down the road, not today. But this explains or hopefully gives you a perspective of what our collision avoidance system can do. It can do this when it sees a full zoomie or sees the barrier as it parks into the driveway. Our main area of concern has to do with turns right now. I need to be able to create a condition where the zoomies can turn and not hit someone else or have someone hit them. And that was the point of this conversation. And as you'll see here, it gets very messy very quickly. Now, right turns are probably our safest, easiest condition for most right turns. All of these here really don't need to be controlled, meaning either a stoplight or even a stop sign. We're turning from the inside lane, turning around the corner to the inside lane, and we do not cross traffic. So this system here, this looks, for the most part, all of this could be done uncontrolled. We don't need a traffic control system. Now let's go to the next. These are controlled right turns. A stop is truthfully required in that, for example, this turn here. It's going from one road entering into the middle of this entire road here. And that's true of every one of these turns here. This is traveling along this road, entering the middle of this road, which goes from here to here. That creates a controlled intersection demand. So as I'm coming up here, we turn right. Well, a Zoomie can be coming from this way and broadside it while it's trying to do that. Or I could broadside, if I'm this vehicle, I could broadside a car going to the right. So I need control for right turns entering the middle of a roadway. That is all the right turns that we can make within ZoomTown. Pretty busy looking mess, but the majority of it is fairly safe. Most of the green ones are fairly safe. The red ones are more hazardous. Now, again, in the US, our left turns will cross a traffic lane. So in the only place where I've got a safe turn where that doesn't happen is out here in the bypass traffic lane. There is no stop, there is no cross traffic. It just simply, the outside track Zoomies can just go and go and go. They have very minimal hazard to them except for cars turning into their lane. So for uncontrolled left turns, this is all I've got, 4 of them. Controlled left turns from one road to another road. And that's what we're showing here. This would be in that same area I was talking about a minute ago. If I'm traveling up this lane, I need to stop, make sure the eastbound traffic is clear and there is no westbound traffic. Then I could travel across the lane and then enter the traffic lane that I want to be in and proceed. Every one of these, we're crossing a traffic lane to get where we need to go. If I'm driving along from east to west, right to left, say I want to turn here. Okay, I turn here, but I got to cross this traffic lane to get onto the roadway I need to be in. So these are all the left turns that should require a traffic stop, controlled, either stop sign or even a stop light. Every single driveway in ZoomTown would also, or could also be entered by a left turn. So here we got a whole lot more areas of high probability of a hazard, a crash. Now this is what it looks like with all potential left turns. A whole lot of red. So this gives you an example of how much traffic management has to be done for this experiment to continually run without Zoomies crashing into each other. A while back, we were talking or mentioning briefly about time and why that's so important in all of this. Here I'm showing you these double arrows with the word 1 sec. Think of that as 1 second of time. So to get from here to here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds approximately. Again, it's close to scale, but not perfect. Now, turning this blue car here, turning left into the driveway, no problem. This one turning left onto a roadway, no problem yet. But let's talk about the red one here, because that'll make, it'll really emphasize my point. If I'm traveling along here and I'm turning left, I can kind of use math and knowledge of where other zoomies are to make sure this area is clear. Now, the time it takes to get from here around the corner and then past the tail end of the zoomie, past this roadway, is 3 seconds. So in 3 seconds, or during a 3-second period of time, I am going to make that left turn all the way across the intersection. Well, if I'm turning in where this red line is, you're probably not even going to see a zoomie in that spot. One could be here, one could be there, or all the way around the opposite side of the block. So if I go to make the left turn into that driveway, I look ahead, I don't see anything, I start making the turn. Well, in 3 seconds, this zoomie could get to there, to there, to there, and hit the zoomie that's turning left. It starts really complicating things when you take into account that time factor. I have mentioned earlier in previous videos that I'm using a graphics library called Pygame in cooperation with the Python 3 programming language. I needed something to handle the graphics. I just defaulted to Pygame. I've used it for other programs I've written in Python, where I didn't need a full-blown GUI, where I'd use Tkinter or something like that. And Pygame gives you a lot of capability in graphics and how you want to handle them. All computer games that you've ever played most likely are using what are called sprites. Sprites are little graphic elements that have special capabilities. We can move them around very efficiently in the computer programming language. They are the code behind them manages the page flipping and so forth and memory flipping to be able to copy an image, copy the background, move the image, replace the background as the sprite moves along. So a sprite is just this little graphic picture that we're moving around on the computer screen. But it has another magical power for gaming. If two sprites bumped into each other, say the little Viking dude here bumped into the little monkey dude here, or maybe the little girl, the Viking, and the monkey and the sword all bumped into each other, the software, part of the Pygame library, any gaming software, would be able to detect when they touch each other, which is wonderful because that's what spawned the idea of where I'm going next. I could use this sprite technology to help make things safe. The important part of this is that we are feeding our position from each zoomie to the scheduler. The scheduler has a pretty good approximate location of every single zoomie. Even as it's moving, it's being updated, we'll say 10 times a second. I haven't got far enough along yet to figure out that frequency based on performance capabilities. But say it's 10 times a second. Each zoomie updates its position so the scheduler's accurate within that time frame. We just mentioned that I can move 8 inches in 1 second. I don't know if I included that in that statement on the time issue, but it's 8 inches for every second at full speed at the present. So in 8 inches, within a tenth of a second, that's 0.8 inches or 20 millimeters. I should be at least accurate that close regarding proximity, which helps us a lot more with trying to figure out if it's safe to turn, etc. And I don't have to do all the math hard-coded. I just let the two sprites figure out if they're going to hit each other, and then it warns me. But that's if they hit each other, say one zoomie would hit the other zoomie. Well, by that point, it's too late, really. There's going to be way too much latency in here. where if I'm just using the image of one zoomie and the image of another zoomie, even if they're scale, the latency of getting the information there and the frequency at which I can update that position, we would physically hit before we could react to slow down relative to the sprite feedback. But like all experiments and thought experiments, you start thinking beyond the obvious, and that's what we're going to cover next. In this graphic image, I'm showing you what I'm calling using a safety shield for crash protection. This green arrow and this green arrow represent two zoomies. The red thing is the zoomie crashing into this pink blob, which I'm calling the blocked zone, and it's actually a sprite, and we're going to use that sprite with its collision detection capability. The sprite for this doesn't have to be another zoomie. It could be any size, any shape I want. So in this case, I'm literally blocking out this whole area and the zoomie can't go in there. Let's start back at the scheduler software. Now the software can detect this collision. The zoomie is not detecting the collision, but the scheduler, if it sees this collision, it can send a command to the zoomie to stop instantly. So the zoomie would stop. A little bit of latency, but my experiments so far showed that it was fairly consistent. I haven't gone into enough detail yet to know how consistent that is. But I could always expand the size of this blockage area or this blocker so that the sprites can't get any further, and when they detect the crash further away from the protected zone, I can respond or command the zoomie to stop moving. Like automatic shields for a Star Wars spaceship or something. So let's see how that would work with some examples here in graphics. Now, this would be a typical left turn. We're traveling along in this lane. This is the blue zoomie. This blue zoomie here is kind of showing the motion of the turn, right? We're going to go through here. This zoomie could easily hit this zoomie. And that's what we're showing with that little red blob there. Well, we don't want that. So when I get to there with this blue zoomie, I get to this location before I start the turn, I could throw down a blocked zone sprite and say, okay, I'm going to turn left here. Let's check to see if there's anything super close mathematically. If not, throw down this blocker. That way nothing can get into this zone, and I'll just go zooming along very happily and very efficiently. And of course, safely. So that's a simple left turn from one road to the start of another. Now I'm turning from one road left onto another, but in the middle of it. Now I got to go across a traffic lane so I could be hit from the car coming from the right or from the left. Again, we don't want the little red blobs, so I would throw down this blob, our blocked zone, and that's using the collision detection. So this zoomie can't penetrate there, nor can this one. And just the nature of a left turn, I've actually got a little extra room for a slow response on this zoomie. Up here, it's a little more immediate because I don't have that extra buffer zone. Backing out of a driveway is another very hazardous because the zoomie backing up is totally blind backing up. It has no rear vision. The cast sensor that we're using is only looking forward. And that maneuver would be back out of the driveway, across this traffic lane, into this traffic lane with the back end of the zoomie pointing toward traffic, so it has no idea what's coming on. Then it moves forward and continues on. See what's happening here? I throw down my blocker and I won't let anybody get near me while I'm backing up. A four-way intersection has always been problematic in the real world, and in a lot of places in Europe for many, many years. I don't know about Asia, but now they're getting very popular here in the United States, are roundabouts. Get rid of the stop sign, let everybody flow and merge together. It's scary as all get out for most Americans still, but we're catching on quick that it's an extremely efficient way to get through an intersection. Unfortunately, my Zoomies, the way they're designed, I can't do a roundabout efficiently or effectively. And even controlling the motion, I think, was a bigger part of the problem. So I stuck with a four-way intersection, which is still very realistic in many parts of the world. But it presents a problem where now, as if I'm the blue car, whether I'm going straight through or turning left, I am exposed to the potential of three Zoomies crashing into me or me crashing into them. Again, the blocked zone can prevent me from hitting them and them from hitting me. Now, you might be wondering, well, if the other Zoomies can't get into the blocked zone, that blocker sprite, how can the blue Zoomie get into it? The software allows me to say which Zoomie can go into the zone and which ones can't. So I can block all other Zoomies, and only the one that's asking for the blocker gets to go through the zone free without worry. Now, if something happens to be in the way, we've still got our cast sensor that could potentially help us in a problem here. But that in and of itself is a problem that we'll discuss in a later video. Now, as I was developing this concept, I got to thinking, well, I'm using these big blobs, and managing that in the software seems simple enough, but if I got to have 2 or 3 different size of those blocker areas, well, now each Zoomie's got to have 3 of those times 16, and suddenly it starts getting more and more complex and more demanding on the sprite control algorithm that's operating it. So it could essentially slow down dramatically. So I just thought, well, let's look at it from another perspective. All I want as I'm going through this intersection is to have no Zoomie enter it until I get through and then release the intersection for others to use. And in the other example, we use a great big huge square blob to block that out. Here I'm using 3 little blockades, kind of like blockades that you see for traffic control in construction zones. Here would be an example of using those as we're backing out of a driveway and then pulling forward. I could turn on that barrier or this barrier or both of them so that nobody can get near me, they can't hit me, and I can't hit them. Now, this will make a little more sense here in a moment, but this is one more example, turning right. I only need to block this guy, so I just turn on that barrier. A turn left into a middle, we would be potentially impacted by both directions, both traffic lanes. And left turn into the start of the next road. We aren't worried about the one behind us because he can see us for the most part, but the one in the oncoming traffic lane, that's the one that definitely needs a blockade or a barrier. Now, this is where the concept is at right now. I haven't even put this in code, whereas the other one I've tested tested in practical, actually. Not good enough because it was only one Zoomie and one blocker sprite. But for this one, this is where I'm starting to lean in my idea. Instead of each Zoomie, for example, carrying around different sized blockers for different intersections, and then when it gets to an intersection, it puts down the appropriate size blocker. That gets to be a bit more difficult to manage for turning them on, turning them off, and the controlling of the aspect that the Zoomie can drive through it, but not the other Zoomies. So managing that data gets more complicated. And I got to have a lot of Zoomies perhaps coming and going from memory. So that one's a little tricky yet. Unfortunately, I'm not masterfully skilled in working with Pygame. I use it primarily just as the graphics language, so this whole gaming part of it is new to me, and I'm using it in a pretty weird way. So I got to think it through. But here's the last idea I came up with. Instead of carrying these blockers with me, these blockers already exist in all these locations. Wherever I think, for example, a stop sign should be, but it's an optional stop sign, meaning it's not on. If it's not needed, it's not on, you just drive through it. Kind of the dream stop sign and the dream stop lights. So here I'm showing our original drawing going from east to west, right to left. This Zoomie wants to turn left here. Well, I've got blockers in each of these locations. Here's one before this driveway, one between these two driveways, one just before this road, one before this driveway, and one before this driveway. Now a Zoomie could be here, going along this way, happy and safe. A Zoomie can be going along here, happy and safe, but as I approach the intersection here, I say we need to turn on that blocker. No one can go past that blocker. So it doesn't even need to know which Zoomies to block, just all of them. When that goes on, this Zoomie can't get through. I then make the turn, get on through to the safe position, turn that blocker off, and then the Zoomies continue again. It's a slightly different paradigm than throwing down a big blob, a whole great big blocker for the intersection, but it does solve problems within programming and managing all that data. And with that, we've reached the end of the road, so to speak. So I would absolutely love your feedback on these different ideas and how you may put a different spin on it if you think it would be beneficial. It's a cool topic of discussion. Hopefully we can share some ideas, and in the course of the next couple of weeks, I'm going to be moving towards implementing this. So if you got ideas, please do share them. That's going to wrap it up for this video. I'm sorry it went literally twice as long as I thought it would. I don't think I could have shortened it up too much, though. Thanks again for watching, and I look forward to seeing you in the next episode.